third part of this chapter deals with simultaneous equations on graphs. It's quite an annoying chapter because you have to draw the graphs accurately to get an accurate answer, which is fine for linear ones, but we've got a quadratic one to do in example 5, which is a bit of a pain. Okay, so on to the first one. Well, what we need to do here is work out how to draw this equation onto the graph. You could use cover-up method and get x is 4, so we know it crosses the x-axis at 4. But if you try to do that with y, you're going to have an awkward one to do, because you're going to get y is 8/3, and plotting that in the graph's not going to be ideal. So let's just think then, we could put, for example, when x equals 1, this is 2, bring that across, you get 3y is 6, y equals 2. So when x equals 1, y equals 2. Then we've got 2 points which we can join up. Let's give it a line. This one, if we, for example, put x equals 1, bring that, so that's 3, bring that across 20, y is minus 20, that's too small. So let's try when x equals, say, 4. When x equals 4, 12, bring that across 9, again too small. X equals 5 maybe, 15, bring that across 8. So when x equals 5, y equals 8, so again that's still too small. What about when x equals 6? When x equals 6, you've got 18, bring that across, y would be negative 5. When x is 6, y is negative 5. What about x equals 8? When x equals 8, you've got 24, minus 1, minus y is minus 1, so y would be 1. So when x is 8, just going off the graph a little bit, y is 1. I should have had a slightly bigger axes. It's just enough to tell me that they cross here when x equals 7 and y equals negative 2. So you can solve simultaneous equations graphically if you plot them accurately. You can just read off the points of intersection. Obviously linear ones should cross once. What about a linear and a quadratic as in example 5? Well, this one we can use the cover-up method quite easily, so y is 3, 2x is 3, so x is 1.5. I'm not particularly happy about a decimal, so what about when x equals 3? When x equals 3, y would be minus 3. Just down there. But it should all line a straight line. You've got to draw it accurately though. Now we know the general shape of this quadratic. It's going to be a smiler. It's going to go through at 1. So it's going to be a smiler going through at 1. We could work out where it crosses the x-axis by solving it, but I don't think they're going to be very pleasant solutions. So I think with something like that, we're probably better off going for a table of values, say from minus 2 to 4. So x1, minus 2, minus 1, 0, 1, 2, 3, 4. So, it's often easy to work backwards. When x is 4, you're going to have 16, take 12, add 1, so it's going to be 5. When x equals 3, you're going to have 9, take 9 is 0, so it's going to be 1. When x equals 2, you're going to have 4, take 6, minus 2, plus 1 is minus 1. When x is 1, you're going to have 1 plus 1, take away 3, minus 1. So we're going to have a repeat there because it goes minus 1, minus 1. Oh no, sorry, that's going to be a 1. That's going to be a 5. And x is minus 2. So minus 2 squared is 4. Minus 3 times minus 2 is 6. So 4 plus 6 plus 1 is 11. So that's going to be off the graph anyway. So if I just plot these ones, so 1, 5, well actually that looks like a point of intersection. 0, 1. I knew that anyway because I know from the general shape it's going to be a curve and it's going to go through the y-axis at 1. 0 is 1. No, I've done that. 1 is minus 1. 2 is minus 1. So again, we've got our second point of intersection. 3 is 1. 4 is 5. Okay, now be careful when you draw this. You don't have a flat bottom, it's going to dip below there. Not the best curve. But anyway, we know the 2 points intersection are here. Oh, it's a bit dodgy there, and here. So we've got minus 1, 5, and we've got what are 2 minus 1. Those are 2 solutions. Now, when you've got a linear equation, a straight line, and a curve, 3 things can happen. They can cross twice, like in this example, or the straight line might just touch the curve, in which case you would say it's tangent to the curve at a particular point, or another straight line might never meet it, might never cut. So you've got 3 situations. You're either going to have 2 solutions where it cuts twice, 1 solution where it touches the curve, or the line might not cut at all. And in order to work that out, I can use the discriminator. So when you've got a linear equation and a quadratic, you need to eliminate y, so make y the subject of the linear one and substitute in, get rid of the y from the quadratic, make the quadratic equal to 0. So you've got an equation of the type ax squared plus bx plus c is 0, and then you work out the discriminant again. If the discriminant b squared minus 4ac is greater than 0, then the line will cut the curve twice. If b squared minus 4ac equals 0, the line will just touch the curve once. If b squared minus 4ac is less than 0, they will not cut at all. There'll be no point of intersection. So it's very, very similar to where we were looking at solutions previously. So let's look at example 6. Example 6, we've got the linear equation, the quadratic equation in terms of k though, which makes it more difficult. We are told though it meets once. We're told there's one solution. That's telling us discriminant is equal to 0. We're also told k is positive. We need to find k, find the point of intersection. So first thing to do is to eliminate y from this equation. So y equals 2x plus 1. So we just need to substitute that straight into there. So if y is 2x plus 1, 2y is 4x plus 2. So we're going to put 4x plus 2 into there. So we've got kx squared plus 4x plus 2 plus k minus 2 is 0. Just tidying that up a little bit. Kx squared plus 5. I don't know, let's say k, isn't it? 2 minus 2 is 0, so plus 4x minus plus k is 0. Now, I know the discriminant is equal to 0, b squared minus 4ac. So a is k. Sorry, I've written that down wrong. It's k x squared, it's the x out. A is k, b is 4, c is k. I know b squared minus 4ac equals 0 because it touches, so there's one solution. So I've got 16 minus 4k, k squared equals 0. 4k squared is 16, k squared equals 4, k is plus or minus 2. However, we're told in the question k is positive, so k equals 2. Now, let's put that back into here, and that tells me 2x squared plus 4x plus 2 equals 0. So if I divide everything by 2, x squared plus 2x plus 1 equals 0, x plus 1 is 0. So there's one solution which we were looking for when x equals minus 1. Don't forget to work out the y coordinate. y is 2x plus 1. So 2x is minus 2 plus 1 is also minus 1. So the point of intersection is minus 1, minus 1. Now what I could have done once I worked out k is 2 is put it back into here and then solve the simultaneous equations to work out the point of intersection. But you've already done that here, so you just be doing work twice for the sake of it. So that's why I substituted it into here, because I'd already done that work. Have a go at exercise 3C.